Hi, I am Artur Saturnino, and this is the first video of a two-part series on capillary surfaces. In this first video, I'm gonna introduce capillary surfaces, and I'm gonna give some recent results that I obtained with my colleague Han Hong, who's gonna present the second video of the series. Before starting, I would like to thank Professor Hojo for the invitation to be here, and I would also like to thank him for inviting me and Han for the first edition of the festival, which is where we met, so he is in part responsible for this work. Now, a capillary surface is a CMC surface with boundary that meets the boundary of ambient space at a constant angle. For an example that occurs in nature, we have these two here, which are the interface between water and air. So always when you have a system with liquids, gas, and solids, and we discount gravity, what we're gonna have here is a capillary surface. So it meets this solid at a constant angle, and it has constant curvature. You notice that this angle here, where the liquid meets the solids, this is an angle that depends only really on properties of the liquid, the solid, and the gas. Now, to get to this definition, we're going to take a route. We're going to talk about variational setup, how we get to this definition, because we want to talk about the second variation and other variants, other quantities related to variation that are going to be important for us. Okay, so the setup for the variation is the following. So let's first consider X, two-sided isometric immersion of a surface sigma with boundary in a three manifolds with boundary M. So for now, we're not assuming that sigma is compact. And we assume that this immersion has the following property, this equation. So what this here is saying is that sigma does not meet the boundary of M in the interior. So there is no interior contact between sigma and the boundary of M. It also tells us that sigma does not have boundary inside of M. All the boundary of M of sigma is in the boundary of M. So now let's consider a one parameter family of immersions with this property. And let's assume that this one parameter family is supported on a compact set omega, meaning that it is constant on T for points outside of omega. I'm going to consider some functionals. The first one is the area functional, which measures the variation of area in sigma. The second functional is the so-called wetting area functional. And then what it measures is, so for example, if you think about an example based on what I had before, where we have this boundary M here be some kind of surface, and we have, imagine that we have some ball sitting over it, then what this wetting area functional measures is how much this area, so the area of the boundary of M that is in contact with this, let's say the interior of this, this cap here, varies in time as we execute this variation X. And the third functional is the signed volume functional. So what this measures is, again, imagine that we have the same setup as before. So we have a kind of spherical cap on a surface, sitting on a surface on RAM. Then what this measures here is how the interior volume varies as we do the variation. I can put the area functional and the wetting area functional together in this energy functional E. Notice that here we also introduce another parameter. This is cosine theta factor, where theta here, we're going to think of it as an angle. It's a value between 0 and pi over 2. And as you're going to see, this translates to an angle. And this, in the physical setup, this theta here really only depends on physical properties of the materials. So as we showed before, we have different angles depending on the material where water is sitting, and depending if it is hydrophilic or hydrophobic. Now we're going to take the first derivative of these functionals. Let's first consider, let's write y for the variational vector field associated to x. That is, y is the derivative in time t for the immersion. And then the first variation of volume is given by the products along sigma between the variational vector field and the outward and the normal nu. And the energy, the first variation of energy, the first derivative of energy is it's given by minus here the integral along sigma of the product between the mean curvature vector of sigma and the variational vector fields, plus, which is, as we always have, for the, if you're familiar with CMC surfaces or minimal surfaces, you know this formula. But here we also have a boundary term, where it's again the product between the variational vector fields and now this quantity here, where this is the conormal, and T is a vector which is tangent to the boundary of M, but which is tangent to the boundary of M and is normal to the boundary of sigma. And it's defined in a direction such that there is some orientation of this set here is equal to the orientation of these two, when here's the outward normal. A capillary surface is then defined as a critical point of this energy for volume preserving variations. That is, for variations where this first derivative of volume is 0. So this means that this quantity on the right has to be 0 whenever this here is 0. This means two things. The first one is that the mean curvature is constant. And the second one is that the angle between the conormal, eta, and t is theta. So this angle appears here and appears here as well. Since a capillary surface is a critical point of energy, it's very natural to want to take the second derivative there at the capillary surface. And this is the second variation of energy. And it's going to be very important for us as we define the index in the next slide. So to do the second variation of energy, we're going to take sigma to be capillary. We're going to consider a volume preserving variation x, and with variational vector field y. And now we're going to write u for the product between the variational vector field and the normal. Then it turns out that the second derivative of energy at time 0 really only depends on u, and is given by this formula here on the right. This first integral on sigma, this should already be familiar with for people that know minimal and CMC surfaces, because this is the same formula for the second variation of these surfaces. This is the interior part. But it's interesting that here we get a boundary part as well that I'm going to talk more about soon. The second variation of energy can be rewritten like this, just by taking integrating by parts, where J is, where this J here is the usual Jacobi operator. Now, using this formula, we can define a symmetric bilinear form Q, which is the stability operator. Explaining this function Q better, notice that this function Q is usually written like this, first here, where H del sigma is the second fundamental form of the boundary of M. And of course, H sigma is the second fundamental form of sigma. But turns out that this can be rewritten just using trigonometry as the second form here, which we use more throughout the paper. In the second form, this H del M is the mean curvature of M with respect to the inverse normal. So for example, if M is a ball in R3, this here is going to be positive. And this here, as I already saw, is the mean curvature of sigma, so it's also non-negative. And this last term, kappa del sigma, is the geodesic curvature of the boundary of sigma with respect to sigma. So it is an intrinsic quantity of sigma. The second variation gives rise to two quantities called the weak index and the strong index. And they're defined in the following way for compact surfaces. So for a compact capillary surface, the weak index is the maximal dimension of a subspace, W of the space of all smooth functions with mean 0, such that Q restricted to the subspace W is negative definite. So what we're doing is basically counting with multiplicity the number of negative eigenvalues of the operator Q in this space V. The strong index has a similar definition, but now the strong index of a capillary surface is here, instead of considering only functions with mean 0, we consider all smooth functions. So as you can guess, these are very much related. So the weak index is bounded above, is bounded above by the strong index. Strong index, of course, going to be usually larger, but it's not that much larger. It's at most a weak index plus 1. Now here we assume that sigma is compact, but a lot of our theorems are for non-compact surfaces. We can also define the weak and strong index for non-compact capillary surfaces, and this is done by exhaustion. So we take compact subsets, compute the index in each one, and take a limit as the subsets grow through the whole sigma. And finally, we say that a capillary surface is weakly stable if its weak index is 0, and strongly stable if its strong index is 0. For some example, the first one is basically a a recap of what I showed in the first slides, and that is a spherical cap in a half space of R3. So it turns out to be the only weakly stable compact capillary surface immersed in a half space of R3 that either has contact angle pi/2, meaning it has free boundary, or that has embedded boundary components. And I believe this is true for Rn, not just R3, due to a result of, and this is due to a result of Ainus and Swarm. The second example is similar, it's now a spherical cap in a ball of R3. And it turns out to be the only weakly stable compact capillary surface immersed in a ball of R3 besides the flat disk. Again, it's due to results of Ross and Vergasta and also Nunes, together with work of Nunes. And this turns out to be generalizable to Euclidean, hyperbolic, and spherical space forms for all dimensions and greater than 3 by work of Wang and Xia. These other examples are non-compact. So the first one is a catenoid cut by a plane perpendicular to the axis of rotation. So you can see this is a capillary surface, and the angle here, the contact angle, is arbitrary because we can change the heights where we cut, and this is going to change the angle. The next example is again a catenoid, but now instead of cutting it perpendicular to the axis of rotation, we cut it by a plane which contains the axis of rotation. This is the angle here. Contact angle is going to be pi/2, meaning that the surface has free boundary. But here is interesting that the boundary is non-compact. And of course, we can do a similar construction for any CMC surface that has an axis of rotation. So now talk about our main results. The first main result is an index estimate, and it's a generalization of work by Ajax and my collaborator, Hong. So for this theorem, we assume that M is a three-dimensional oriented Riemannian manifold with boundary embedded in RD, where D is some integer. Of course, this can always be done. And we're going to take sigma to be a compact capillary surface immersed in M at a constant angle theta, and we're going to let G be the genus of the compact cap of this surface, and R be the number of boundary components. And here we're going to suppose that for every non-zero harmonic vector fields of sigma that is tangent to the boundary of sigma, this inequality here, this big inequality here, is satisfied. Here in this inequality, this term is the second fundamental form of M in RD. Rm is the scalar curvature of M. And notice, for example, that this here always hold as long as this H, the mean curvature of sigma, is large enough with respect to these other values associated to M. Another example that we're going to see where we can verify this inequality is when M is a domain of R3, plus some additional assumptions, of course. Okay, so given this inequality, we have a lower index bound for the index of sigma, which depends only on the genus and the number of boundary components, which is a type of result which is which is recurrent in the study of index of CMC surfaces and minimal surfaces and so on. We like to see these index bounds because they gives us a relationship between the index, which is a variational quantity, and the topology of the surface, which is something that is usually not that trivial to obtain. But it's also a nice relationship. So the second result also, okay, so this is the particular case in R3. Now we assume that M is domain in R3. Then to verify that big inequality, we suppose that this quantity here is non-negative. So it's H del sigma plus H sigma cosine theta, which again, this here is the term that appears on Q. Q is equal to 1 over sine theta times this here. I believe then minus kappa del sigma. So this is why this quantity here appears here and appears all the time. So again, assume it's non-negative and assume that either sigma is non-minimal or that the mean curvature of M is greater than 0 at some point of the boundary. Then we can verify that inequality for D equals 3, and we get this following index bound. Okay, the second result is an analog of a classical result of Fisher-Colbury for minimal surfaces, and this relates the index to the conformal structure of capillary surfaces. And as you're going to see, this has a lot of interesting applications. This really opens the door for some of our other results. So we assume that M, again, is an oriented Riemannian tree-manifold, smooth boundary. And I can assume now that sigma is a non-compact capillary surface with finite index. So finite index means either finite weak index or finite strong index. They differ by 1, so one is finite if and only if the other one is. Again, immersed in M, the constant angle theta, and we assume that the scalar curvature of M summed with the square of the mean curvature of sigma is non-negative, and that one of these holds is either the boundary of M is compact or that the same inequality that we had before holds along the boundary of sigma. Then we conclude that sigma is conformally equivalent to a compact Riemannian surface with boundary and finitely many points removed. So a surface, so meaning that instead of, we're not removing disks here for each end, we're just removing points, which is very nice for constructing functions. So for example, let's do some examples. The first example is the catenoids that represented. So a catenoid cuts by plane orthogonal to the axis of symmetry, and that is conformally equivalent to a closed disk with an interior puncture. So the boundary of the disk corresponds to the boundary of the catenoid here, and this puncture corresponds to this end of the catenoid. For the other example, so again the catenoid, but now we cut it along the axis of rotation. Well, that turns out to be conformal equivalent to, again, a closed disk, but now instead of a single interior puncture, we have two boundary punctures, each of which corresponds to an end, one of these two ends here. So we call these ends in the boundary ends, and we call the ends in interior ends. For more about it, see the second video of the series. Okay, so this is gives us a nice description of the ends, and more than that, we also have that these surfaces have finite total curvature. The integral of the second fundamental form squared is finite, and we also have that the integral along the boundary of this quantity here that always appears is going to be finite as well. So again, relating the index to the geometry of the surface. So one of the nice things about the structure that we get from the last theorem is that it allows us to apply the log cutoff trick. And apply the log cutoff trick to a suitable test function. And what we do then, we define a suitable test function to show the following result here. So we assume now that sigma is a non-compact capillary surface immersed in a half space of R3 at a constant length theta. And we assume that this constant here, h sigma cosine theta, is greater or equal to 0, which is just a version of that same assumption that we always have. Then it turns out that sigma is strongly stable if and only if it is a half plane. Let me note that here on our preprints, we say strongly stable, but now we know that this is true if it is weakly stable. This can be relaxed to weakly stable. And Han's going to present this result on the second talk. And to make a relation with the theory of CMC and minimal surfaces, we know that the only non-compact CMC surface immersed in a half space immersed in R3 is a plane. So this is kind of bringing an analogous results to the context of capillary surfaces. And of course, this is always a very natural question to ask: what are these stable surfaces? So this gives us at least a partial answer given this assumption. This characterization of the stable surfaces, together with some ideas of Rosenberg, Sohm, and Tobiana, allows us to prove also curvature bounds for strongly stable capillary surfaces. So explaining here how these bounds work. So first we fix an angle. And now it turns out that there is a constant C depending only on the angle. So it's nice that this is the only dependence, such that the following here holds. So whenever M is a tree manifold with smooth boundary, and we assume that M has curvature bounded above by lambda and injectivity radius bounded below by iota. So here curvature bounded above by lambda means sectional curvature bounded above by lambda, and also means bounds on the second fundamental form of the boundary of M. And this injectivity radius bounded below by iota has some meanings which I will just refer to the paper, but the idea is really injectivity radius bounded. So notice that here we don't really assume that M is compact, but we assume that it has finite geometry in this certain sense. And now we assume that sigma is again a strongly stable, edged capillary surface immersed in M at a constant angle theta. Edged here means that sigma might have an interior boundary. So it might have a boundary which is the interior of M, which is, and we assume that this boundary is fixed on our variations. Again, so see the paper for a more precise definition. But then turns out that we divide in two cases based on the value of these constants. The first one, if this constant is non-negative, then we have bounds on the second fundamental form, which depend only on distance to the edge, on the bound on the injectivity radius, and the mean curvature bound, and the bound on the curvature of ambient space. In the second case, where this constant is negative, we have bounds on the second fundamental form, which depend on all that we had before, but also depend on the mean curvature. So the idea for this technique is really, it comes from the theorem we just presented before, the uniqueness of the half plane, because this is really about scaling. This is about scaling, looking at the surface sigma at the scale of its second fundamental form, and then using that it is strongly stable in order to conclude that it has to be a plane, after taking a limit. It is a technical argument, but the idea is pretty straightforward. And it's just again, a generalization of a classical result by Shane. And this kind of curvature bounds appear everywhere in the study of minimal and CMC surfaces. Now, notice that this first bound here, the second fundamental form doesn't enter the left-hand side, doesn't enter here. So, sorry, the mean curvature doesn't enter in this part here. And this is nice because it lets us conclude this following corollary. So now assume that the angle is between 0 and pi over 2. We assume all the same things as before, except that now we don't assume that sigma is strongly stable. And we assume this following here. We assume that the mean curvature of sigma is large enough being defined by being greater or equal than this quantity. So as soon as this mean curvature is large, what we get is bounds for the intrinsic distance between any points in sigma and the edge, which are given here on the right-hand side. So this distance can grow at most linearly with the strong index. And we get diameter bounds for the surface, for intrinsic diameter bounds for the surface, which again grow linearly with the index. And the idea here is really just using the inequality that we had before together with some basic geometry and partitioning the manifold in the correct way. So this is all that I have to talk for now. My colleague is gonna is going to present a second video with some more details on some of these proofs. Thank you for attention. If you have any questions, please feel free to ask them. And I hope to see some of you in the Q&A session.